Autonomous AI workflows can make decisions, call tools, and update data without waiting for us. That power creates new attack paths. In this module, we'll learn how to map what matters, identify where trust breaks, and anticipate how attackers could exploit those gaps. Now that we've seen why autonomy, tools, memory, and planning create security risk, we'll turn that understanding into a practical threat model. We'll map workflows, assets, inputs, tools, and attacker goals, then use that model to guide the vulnerable agent baseline we build next. Threat modeling gives us a disciplined way to reason about agent risk. Start with the assets: data, permissions, tools, and decisions the agent can affect. Then define boundaries, such as where user input, memory, APIs, code execution, and human approval cross trust levels. Next, trace the flows, because attacks often travel through normal interactions. From there, ask what an attacker wants: data theft, tool misuse, policy bypass, or harmful actions. Finally, map controls to those paths. The goal is not perfect prediction. It is finding the highest impact risks early enough to reduce them. An autonomous workflow is more than a model answering a prompt. The user may enter through an app, but the real activity happens in the agent runtime, where the system observes context, reasons about a goal, acts through tools, evaluates the result, and responds. Around that loop are prompt templates, model providers, memory stores, APIs, databases, and external services. Each connection can carry sensitive data or influence behavior. So security analysis has to cover both the architecture you designed and what actually happens during repeated runtime decisions. Before you can protect an AI agent, you need to know what protection means. Assets are not just files or databases. They include anything the agent can read, create, change, trigger, or reveal. Sensitive data is the obvious category: credentials, customer records, contracts, code, and private messages. But agent instructions are assets too, because they shape behavior. So are operational capabilities like sending email, writing to a database, running code, or initiating payments. Long-lived context also matters: memory, embeddings, logs, and history. If it has value, impact, or privilege, identify it. A trust boundary appears whenever information crosses from one security assumption to another. That includes obvious inputs, like user messages and web pages, but also less obvious paths, such as tool results, memory retrieval, database reads, and model provider responses. The key lesson is that authentication does not automatically create trust. A signed-in user can paste malicious instructions. A trusted tool can return compromised data. Every crossing needs validation, permission checks, logging, and clear limits on what the agent may do with what it receives. Prompts and memory deserve the same protection. With agents, we need to model two flows at once. Data flow asks where information comes from, how it is transformed, where it is stored, and where it leaves. Instruction flow asks what can influence the agent's decisions, including prompts, policies, tool directives, and prior outputs. Prompt injection exploits the boundary between those flows. A web page or email may look like data, but contain instructions the agent might follow. So threat modeling must label origin, sensitivity, destination, and whether the agent is allowed to act on that content. Here, the key shift is that model output is not the same as real-world action. A mistaken answer may be harmless until an agent can send it as an email, issue a refund, update a CRM, run code, or touch cloud infrastructure. That tool boundary is where risk changes. Evaluate each tool by permission scope, reversibility, business impact, and who else is affected. Read-only search is very different from database writes or shell access. Threat model tool access separately and put stronger controls around actions that are destructive, external, or hard to undo. Effective threat modeling also starts with attacker intent. In autonomous workflows, the danger is not only that a model gives a bad answer, it is that an attacker steers the agent toward a business outcome. They may try to steal prompts, records, credentials, or code. They may misuse tools to send messages, move money, change records, or call APIs. They may escalate privileges from a harmless interaction into an administrative action. Or they may manipulate the workflow itself by bypassing policy, approving fraud, or changing decisions. Controls should map to these objectives. An attack scenario turns a vague risk into a testable story. Start with the attacker's entry point, such as a web page, email, or support chat. Then name the asset they want, the boundary they cross, and the agent behavior they manipulate. The scenario should end with a concrete impact, like leaked notes or an unauthorized refund. Good scenarios are not science fiction. They are realistic chains that expose where controls are missing. That makes them useful for writing tests, choosing logs, limiting tool access, and proving whether safeguards actually work. Severity scoring turns concern into action. For agent threats, do not rank risk by impact alone. Combine impact, likelihood, exploitability, detectability, and reversibility. A leaked prompt may be embarrassing, but an unauthorized refund or production database change can create lasting damage. Likelihood rises when agents read untrusted content, hold broad tool permissions, or skip validation checks. Reversibility is often the tiebreaker. Sending emails, deleting records, issuing payments, or publishing content may be hard to undo. Use the score to choose the response. Accept low risk, test medium risk, require approval for high risk, and add immediate controls for critical risk. A threat model is only useful when it drives decisions. For each meaningful risk, identify the asset exposed, the boundary involved, the likely impact, and the owner of the response. Then map controls in 3 layers. Preventive controls reduce the chance of failure. Least privilege, validation, sandboxing, and allow lists. Detective controls reveal when something is going wrong. Logs, monitoring, anomaly detection, and trace review. Corrective controls support recovery. Rollback, revocation, playbooks, and policy updates. Prioritize severe risks, especially tools that can change external systems or cause irreversible effects. For high-risk agent actions, the key principle is separation of judgment from authority. The agent can propose an action, but independent controls decide whether it may run. Policy checks screen intent. Validation confirms inputs, outputs, destinations, and requested operations. Sandboxing limits damage if code, files, browsers, or tool calls behave unexpectedly. For sensitive or irreversible steps, a human approval gate pauses execution. If any requirement fails, the action is blocked and logged. This creates a system that is enforceable, auditable, and trustworthy beyond the model's own reasoning. An agent threat model should be treated as a living control because the system it describes keeps changing. New prompts, tools, permissions, memory rules, models, data sources, and deployment environments can all create new attack paths. Keep the model current during design reviews, before release, after deployment, after major changes, and after incidents. Then feed reality back into it. Logs, evals, red team findings, and incidents reveal failures you did not predict. Mature teams connect the model directly to tests, monitoring rules, response plans, and future engineering decisions. Threat modeling helps us slow the agent down before risk becomes reality. Identify the assets worth protecting, trace how data crosses trust boundaries, and ask what an attacker would try to achieve. Then connect each risk to practical controls and monitoring. Next, we'll build a vulnerable agent baseline so you can test these ideas, break workflows safely, and harden them.